Salutations. I want to review the quiz number 10 with you on Euler equations. So these are equations of the form ax squared y double prime plus bxy prime plus cy equals 0. So don't confuse these with constant coefficients because there would be no x squared and x in there. And the powers of x have to be this way, otherwise it would not be considered an Euler equation. Okay, and then to this we have to, instead of characteristic polynomial, we have the initial polynomial instead of these, and the division in between discriminant 0, bigger than 0 or less than 0 is the same, but the form is slightly different. So let's look at some examples. So here's the first one: x squared y double prime plus 8xy prime plus 12y equals 0. Okay, so the initial polynomial, and it's of course very important that you know how to do this. You look at this term, x squared y double prime becomes t to t minus 1. Replace that by t to t minus 1. This xy prime you replace by t, and the y you replace by nothing, by 1. So that's the initial polynomial. So this is t squared minus t plus 8t plus 12, that is t squared plus 7t plus 12 equals 0. So we need two numbers that multiply to 12 and add up to 7. 3 and 4 do the job. So we get t is -3 and t is -4. This is the straightforward one. We have two different roots. Discriminant is positive, and we know that the general solution is these become exponents of x. So x to the power -3 plus b times x to the power -4. Okay, so these are very simple form. But once we have it slightly different, so let's do another one here. I'll do one of each type so that you get a little bit the flavor of everything. 4x squared y double prime plus 16xy prime plus 9y equals 0. So again, the initial polynomial. That would be 4t times t minus 1 plus 16t plus 9. So that is 4t squared minus 4t plus 16t plus 9. So that is 4t squared plus 12t plus 9. Now this one we can factor too. Let me show you how to factor. You might see actually the solution here because it's a special form, but let's just do the AC method. Of course you can also use the quadratic method, but AC method. So we need two numbers. So AC is equal to, this is A and this is C, right? So that's equal to 36, and B is equal to 12. So we need two numbers that multiply to 36 and add up to 12. Well, that is 6 times 6 and 6 plus 6, right? So what this means is we're going to write B now. So we write this as 4t squared. We split the 12 as 6t plus 6t. Two numbers that we found. And then we group. So we group this here and we factor out the 2t. And what is left is a 2t plus 3. And here we factor out the 3, right? And so what we have left is 2t plus 3. And this is what has to happen. This has to have the common factor. So you get 2t plus 3, factor that out, and what is left, here is the 2t, and this is the 3. It's twice the same. So this is actually 2t plus 3 squared. So as I said, some of you might have recognized this is a double product formula. So what does this mean is the discriminant is 0, so this is a special case, and the root is 2t plus 3 equals 0, so that means that 2t is equal to -3, so t is equal to -3 halves. What does that now mean for the general solution? So the general solution now, well, that will be, again, the exponent for x, but we cannot take it twice because that will give me the same thing. I need something linear independent, and that's where the ln x comes from. So we have an a plus b times this guy. Okay, and then I want to do a third one. X squared y double prime plus 7xy prime plus 13 equals 0. So the initial polynomial here. Okay, so in this one I'm going to do an initial condition. I'm going to do y1 is 12, and that's also going to be the derivative at 1. Okay, and I'm looking the Euler solution. Okay, let's call it the Euler solution. So I'm solving this as an Euler polynomial, and then you'll see why I'm saying this, because I'm going to do the other one as well. So the initial polynomial, that is t times t minus 1 plus 7t plus 13, that is a t squared. This is minus t plus 7t plus 13, so that is t squared plus 6t plus 13. So what we need to do now is, well, you can find the quadratic formula, you can find, so there's two ways. Either you try to factor, but two numbers multiplied to 13, they never add up to 6, that's almost immediately clear. So what we need to do is either quadratic formula, or I'll show you completing the square, because completing the square is something that you're going to have to do in chapter 8 as well. So let's do it, review it quickly. We take the two terms that have a t in it and write the other term a little bit further, because we're going to insert something here. What are we going to insert? Well, we divide this by 2, and that gives, in this case, 3. Okay. And then we square this thing, so we get a plus 9 here. Now if I add 9, of course I cannot do that, I subtract it again, so keeping the balance. And then we know that this is t plus 3 squared, this is 3, right, that's where the 3 comes from, and this is of course plus 4. Okay, so that's, so now we put this equal to 0, then t plus 3 squared is negative 4, so t plus 3 is, now we take the square root, but of the minus 1 gives me, we have plus minus square root 2i, of course, there's an I now because of the negative sign, and so we see that t is equal to minus 3 plus or minus 2i. So this is again, lambda is minus 3 and omega is 2. Why is this important? Well, we know in this case, as in the constant coefficients, we are dealing now with trig functions. But again, the form is slightly different. First of all, this lambda is going to give me the power, and this is x to the minus 3 again. What does the omega do? Omega is giving me the frequency, so this will be cosine 2, but we don't put in x here, we put in ln x. That's the one difference. Plus sine, so this is, okay, a times this, plus these are general coefficients, like plus b times sine 2 ln x. Okay, that's how this general solution looks like. Okay, we had an initial condition, there was 12 in both, right? So if x is 1, then y is 12, and y prime was also 12. So this means the 12. We know that the ln, any power of x of 1 is 1, and the ln of 1 is 0. So the only term that survives is the cosine of 0. So that is 12 equals a, that's it. So 12 is a. Right, so that's what survives, right? Now we need to take the derivative. This is a product, so we can do the product rule. You can also do the quotient rule, but I'm not in favor of that. So I told you already many times. That is the result of taking the derivative of the inside function. Sorry, of the first factor. I'm already thinking ahead, right? Plus, now I copy the first factor and I have to take the derivative of the second one, but there is an inside function, so we get a times the derivative of cosine is minus sine 2 ln x, plug in the inside function, and then take the derivative of the inside function, that is 2 over x. And the same here, b, the derivative of sine is cosine, plug in the inside function, and then multiply with the derivative of the inside function, 2 over x. Okay, so again, the signs will disappear if I plug in 1, because that's the ln of 1 is 0. So I'm left with 12, this is y prime, sorry, I write y, but it's y prime, of course. 12, the same value, is minus 3 a, this one survives, this one is gone, this one is gone, but this one survives. That is plus b times, no, be careful, there's an extra 2 here on the bottom, at the back. So this is 12 is equal to minus 36, because 12a was also 12, plus 2b, so we see that 2b is equal to 48, so b is equal to 24. And so our solution was y equals x to the minus cube, or you can, let's write it even neater and write it as a denominator. So we have, oh, that's the wrong color. Let me bring this back up here. Okay. y is, yeah, I was going to write it as x cubed here, and on top we had 12 cosine 2 ln x plus 24 sine 2 ln x. Right, it was sine and cosine, right? A and b, yeah, okay. All right, so that is our Euler solution. Now, on the quiz, I will also ask you to do something else. Because, okay, this is rather short, right? I mean, I did now 3 problems in a short time. So I'm going to ask you a second part, saying, and let's look at the exact same equation here, and even with the same initial conditions. It might be that I take different initial conditions, but here I'm going to just, for simplicity, take the same initial conditions. But now I'm looking for a power series solution. Now you say, Professor, you told us it doesn't exist because this is an ordinary point, is a singular point, it's not an ordinary point, it's a singular point. Well, when? When x is 0. So yes, the power series with center 0 does not exist. But any other point is an ordinary point, so it will have a power series at that centered at that point. And what the initial conditions now indicate that my center actually is supposed to be 1. So I can do this. So now I'm looking, instead of looking, so this is the Euler solution, or the solution to the viewed as an, so now I'm going to look for a power series solution. But as I said, centered at 1. So this means something of the form, of this form. Okay, and you'll see it exists, of course, because the theory says it, as far as 1 is an ordinary point, so we can do this. So what we need to do? Well, we need to rewrite these coefficients now, right? So the x squared should be written. So x squared, that is x minus 1 plus 1 squared. Remember, we have to now expand everything as polynomials in x minus 1. So that would be x, this is equal to x minus 1 squared plus 2 times x minus 1 plus 1. We also have an x, which is an x minus 1 plus 1. Okay, so our equation becomes, where's the equation? 7 and 13. Okay, let me remember this. So it is x minus 1 plus 1. No, sorry. I'm writing it. X minus 1 squared plus 2 times x minus 1 plus 1 times y double prime plus 7, right, or 7, x minus 1 plus 1 times y prime plus 13, what was it, 13 and 12? 13 plus 13y. There's nothing here, so that's what I'm doing. And now I'm going to have to plug in the derivatives. I'm going to do my derivatives in my head because this is always the same, right? So I hope that's for everybody clear that this is just this guy, the double derivative. Plus 7 times x minus 1 plus 1 times summation n, now just a single derivative, n x minus 1 to the power n minus 1 plus 13 times summation a n x minus 1 to the power n. Okay, we expand. So the first one will give me 3 terms, right? And of course, sorry, and I'm going to combine, expand and combine the powers, right? Sorry, so this, I shouldn't write this here. Okay, so we get summation n minus 1 a n, and then the power is now n. The second term gives me summation 2n minus 1 a n x minus 1 to the power n minus 1, and the last one gives me n minus 1 a n x minus 1 to the power n minus 2. Then this expansion gives me plus summation 7n a n x minus 1 to the power n plus summation 7 n a n x minus 1 to the power n minus 1. And then finally we get plus summation 13 a n x minus 1 to the power n. There are some shifts that we have to do. The first one needs no shift, so and so now I'm going to write everything. I'm going to do the shift, and then I know what the coefficients will be, right? So this needs no shift, so this is going to be just n minus 1, an. For this one, I have to shift n by n plus 1, so this will be plus 2 times n plus 1 times n, an plus 1, okay? The shift for this one is, I need to do it twice, shift up 2, so that is plus n plus 2 times n plus 2 minus 1, n plus 1, n plus 2, and now I have the right power. The next one requires no shift, but then this one requires again a shift of this nature here, right? The same shifting up 1, so this would be plus 7 n plus 1 an plus 1, and then the last one doesn't require a shift. Okay, so let's group now everything. We know that each of these coefficients now have to be equal to 0. So I'm now also going to expand, write them in ascending order here. So an plus 2. So what is the coefficient of an plus 1? Well, we have it here. That's a 2n squared plus 2n, right? If you expand this whole thing here. And we also have it here. Plus 7n plus 7, that's this one, and then we have the an, the coefficient of that one, there's this one, that is n squared minus n, there is this one, plus 7n, and there's this one, plus 13, and I should have now all, okay, have all, good, and this is equal to 0, so this, let's combine this, is 2n squared plus 9n plus 7. This is n squared plus 6n plus 13. Yes, okay. So our conclusion is an plus 2 is equal to minus, right, because I'm going to have to bring the other two guys to the other side, 2n squared plus 9n plus 7 an plus 1. Plus the minus in front of the whole thing, so I don't have to copy the minus here, plus, let me write the factor first, plus n squared plus 6n minus plus 13 an, and that all over n plus 2 times n plus 1. Okay, so this is now a recursion formula. We know that in this case, from the previous quiz, right, that we need to first have a recursion relation. And I want you to do this in this quiz too. All the steps again. No skipping steps. And so in some sense it's a repeat of quiz 9. It's actually a bit more now because you're going to have to do the Euler equation as well as this one. And so then I want you to fill in up to a certain degree. Let's say up to degree 3 or 4. That doesn't make... Okay, let's look at, so the first one would be n equals 0. So we make our table here. So I don't know why I draw my table with one more column. I've never understood why I do this. So okay, we have A0, A1, A2, A3, and A4 say. So A0 was, they were the original ones, right? As I said, I didn't change them. I could have. They were 12 and 12. Okay, yeah, right. So now these here, they become the coefficients A0 and A1 in the power series centered at 1. Okay, otherwise there's something else, right? But okay, here they become, so this is 12 and 12. So if n is 0, that will give me A2. Then I get minus. There's a minus sign. Then on top we have 7 times A1 plus 13 times A0 over 2 times 1, that is 2. Okay, so that is 20 times 12, right? That is minus 20 times 12 because A1 and A2 are both 12 over 2, so that is minus 120. Okay, A3, how do we get A3? Well, that is from n equals 1. So we plug this in, so minus, if I plug in 1, I get 16, 18, 1 plus 1 is 2, plus 1 plus 6 plus 30, 16, 19, 20 plus 20 times a1 over 3 times 2. Okay, so this is minus 18 times 1 minus 120 plus 20 times 12 over 6. Let's divide already by 6 here, so I'm dividing by 6 here and here, right? If I divide in a sum, I have to divide all terms by that. So that becomes then minus, the first one is minus 360, the second one is plus 40, right? Don't forget there's a minus sign in front here, that's at this spot here, right? Okay, and so yes, that is therefore minus, okay, so this is minus 320, so minus minus becomes 320. Okay, A4, that's n equals 2. In A4, all right, so it gets a bit, the numbers get a bit big here, but that's just, okay. 8 plus 18 plus 7 times A3 plus 4 plus 12 plus 13 A2 over 4 times 3, that's 12. Okay, so that is minus 16 plus 7, that is 23 here, right? No, 26, no, 33. 26, 33. 33 times A3, which was 320. There's still a minus sign in the whole thing, right? So there's a 12 in the denominator. Plus 25, 29 times A2, which was minus 120. And everything divided by 12. Again, I can do the division by 12 here. If I divide here, I get minus 10. If I divide here, 320 divided 12. No, that doesn't work. Oh, okay. I can divide this factor here by 3, that was 11. And then I have 4 left. And then I can divide this as 80. That's gone. Okay. So we find minus, and this 11 times 80, that is 880, minus 290, so that is 880 minus 290 is 6 is 590, and there's a minus sign in front of it. Okay, so minus 590, I guess. I could have made a mistake here, but so what is, however, now compare. So we have, this is a function, and it actually converges, it is defined at 1, right? Because we had the initial conditions there. So this is a solution that is, it includes 1. It's a solution that's defined on an interval including 1. Now this series here with the coefficients that we have partially at least calculated, but this series is also a solution. The series with our coefficients that we have is also a solution that is also defined at 1. So sometimes you can have different types of solutions. You get power series solutions or real solutions like the Euler solution, and it depends a little bit on what you're interested in, which solution you would work with. I wanted to do this in this quiz that you should be also aware of the fact that it's not just one method to solve the equation, and it gives totally different answers. They are not comparable at all. One is a power series, the other one is something involving cosine, sines, and logarithms, right? No, what was it here? Where was the here? This one. Look, they're so different. But yeah, this is how things are in differential equations. This is the type of stuff that you can find there often. Okay, so for the review, and I will ask so to do both. So if you feel a little bit sketchy on this second part here, well, look also at the review of the previous quiz.